Okay, let's look at our regio and stereochemistry. Regiochemistry again is which region of the molecules things are going. So our regiochemistry we've already talked about. The regiochemistry is we get anti-Markovnikov addition. Regio is which carbon gets the hydrogen and which one gets the OH. That's your regiochemistry. Let's take a look at the stereochemistry. Okay, we have the borane, THF. We know which carbon is going to get the hydrogen, which one's going to get the boron. That's the regiochemistry. So of the double bond, hydrogen is going to fit in at the more substituted site because it's smaller, and the larger boron will go to the least substituted carbon of the double bond. And while we're doing this, let's look at stereochemistry. Now, we saw as the hydrogen and the boron added, they added at the same time. Or mechanism, they added at the same time. I'm going to draw two different ones here. When you're adding the BH3 boron to the double bond, the first one I'm drawing here is if it's added from underneath, and the second one I drew is where it added from the top. Which one do we get? Both of them. Why? Because we started with a trigonal planar molecule. Alkenes are planar. Those are sp2 carbons. When that borane adds, or double bond, those are sp2 carbons, it's flat. I'm trying to make chiral centers out of an achiral molecule. Anytime you do that, you're going to get a racemic mixture. This starting material is just as flat as this folder is. When the borane adds, it does not matter which side it adds from because it's flat. Our alkene is flat, just like the carbocations were flat when we did those earlier. This is flat. So when we make chiral centers from a flat molecule, an achiral molecule, you're going to have a racemic mixture. I get a 50-50 mixture of these two. Those are enantiomers. We get a 50-50 mixture of the two enantiomers. Now, the last step with the hydrogen peroxide and base I mentioned that this is a replacement reaction. It is not a substitution. Not 100% certain on the mechanism, but we do know that it just replaces and not substitutes. The replacement is that we get an OH in that replaces, probably going through radicals, but it replaces the boron. It's not a substitution, it's a replacement. We keep the same stereochemistry. If it were a substitution, we should get inversion and configuration. But we know, by doing the reaction, we know we don't get inversion. There's the first one. That OH replaces the boron and it keeps the same stereochemistry. We'll also do it on the second one there as well. So we do know that it's a replacement and not a substitution. So we still get the racemic mixture. Okay, so that's the hydroboration followed by the oxidation. We get antimacovnikov addition of water to the double bond. So we've talked about 3 ways to make alcohols from an alkene. Let's just kind of summarize these 3 that we've done today. We first talked about doing a hydration of an alkene to make an alcohol, adding water to an alkene to make an alcohol. We first talked about the acid catalyzed hydration. That was the first one we did there a moment ago. This gave a Makovnikov regiochemistry. The bad thing about this one is you may get rearrangement because there's a carbocation involved. To watch for cation rearrangement. As far as stereochemistry goes, there was no control of stereochemistry. In other words, if you create a chiral center, we will have a racemic mixture. If you're making a chiral product, it will be racemic because we're going through an achiral carbocation. Now we don't always get a racemic because we're not always making a chiral center. But if you make a chiral center, it will be racemic. You'll have a 50-50 mixture of the 2 enantiomers. So there's no control on the stereochemistry part. We talked about the oxymercuration, demercuration. The big advantage, well, first, it does follow Makovnikov regiochemistry just like the previous one did. So when we're adding water to the double bond, the hydrogen goes to the carbon of the double bond with the most hydrogens already on it. The OH goes to the other. The big advantage of this one is it avoids rearrangement. Because there's not a full carbocation involved. The mercury stabilizes it. It holds it in place. As far as stereochemistry goes, no control on stereochemistry. So again, if you make a chiral center, if your product has a chiral center from adding the water, we will have a racemic mixture. We don't always make a chiral center again, but if you make a chiral center, it would be racemic. You'll have a 50-50 mixture of the two enantiomers. And then finally, we just did the hydroboration oxidation. This one gives anti-Markovnikov regiochemistry. That's the big advantage of the hydroboration oxidation. It's different from the others. We get the anti-Markovnikov regiochemistry. As far as stereochemistry goes, we do get syn addition. We have a little control, but with the stereochemistry, we do get syn addition. So the hydrogen and the OH that you're adding will add to the same side. That's syn addition. But other than that, we still get a racemic mixture if you create a chiral center. So we got some control, but not full control. We're still going to get a racemic mixture. But we can control that you do get control of the hydrogen and the OH add to the same side. So like we did the ring there a moment ago. The hydrogen and the OH added to the same side of the ring. Okay, that is our three ways to hydrate an alkene. Add water to an alkene. We're going to skip the next section, section 10. And I'm going to go ahead and just stop there for the day. We'll next be we're going to look at adding some more things to alkenes. And then finally at the end of the chapter, we'll look at adding things to alkynes. But we're going to be looking at adding a few more different things to an alkene. Just keep up with this stuff. You know, it's easy to get lost if you get behind on this. It's just hard to catch up. So please stay with it. These are easier reactions, I think, than what we did on the last test, but it's just going to be a lot of reactions. There's just a lot to keep straight. We don't have all the choices, though. So we're going to begin today by looking at the addition of bromine and chlorine to alkenes. And we're only going to do bromine and chlorine. Of the halogens, those are the two most reactive. Well, not the most reactive. Fluorine is the most reactive, actually. But fluorine is too reactive. If you do fluorine, the reaction will get out of control. They're very exothermic. They give off a lot of heat. And the reaction will get out of control and they typically explode. If you ever meet a fluorine chemist, I can just about 100% guarantee you that he is missing a finger or a hand or an arm or an eye or something. And I say he because women are smart enough not to do fluorine chemistry. So you don't want to do, typically don't want to do fluorine chemistry. So of the halogen molecules, it's the most reactive, and then chlorine, and then bromine is a little bit less reactive than iodine. We don't do it because it's so unreactive. It doesn't want to react in these. So we're going to stick with just the chlorine and bromine. Fluorine too reactive, iodine is too unreactive. So we're going to take an alkene, and we're going to add a chlorine molecule to this. And you get chlorine adding across that double bond. There's our product. You can do the exact same thing. We'll look at the mechanism here in a moment. You can do the exact same thing with a bromine molecule. You'll get bromine adding across the double bond. So you can do the exact same thing with bromine. Now, let's talk a little bit about the mechanism. I'll do the chlorine there for the mechanism. It's the same for either one. Now, these halogen molecules, chlorine or bromine, they're not like what we've done in previous sections. Previous sections we were adding things like hydrogen halides. If you add a hydrogen halide to the double bond, this makes sense. There's partial negative on the chlorine, partial positive on the hydrogen. So the electrons in the double bond are attracted to that partial positive. We protonate it and go on from there. But if you look at a chlorine molecule or a bromine molecule, you have the exact same electronegativity. So why would the double bond want to react with that? Even though there's the exact same electronegativity, if you had just chlorine or bromine by itself, there's no partial positive or partial negative. But as a chlorine or bromine molecule gets close to that double bond, there's so many electrons here. You got 2 in that bond, 2 in that bond. So you got 4 electrons right there in one little tiny spot. And on the chlorine molecule, you have all these lone pairs of electrons. So the electrons in the double bond and the electrons in the chlorine molecule or bromine molecule, they're going to repel each other. They don't like each other. They repel. So as the chlorine gets closer and closer to the double bond, you get a buildup of partial negative on the one that's the furthest away and partial positive on the one that's the closest to the double bond. It's just because the electrons are repelling each other. So it's got nothing to do with electronegativity here, like we had with HCl or HBr. This is just electrons repelling. So eventually we get enough buildup of separation of charge that eventually the electrons in double bond will come out and grab that chlorine with the partial positive, and we'll kick the electrons out of the chlorine-chlorine bond onto the other chlorine atom. So one of those 2 carbons of the double bond gets the chlorine, and in this example it does not matter which is which. The other one will get a plus charge because the initial tail becomes more positive by charge. We can kick the chlorine off. So we get a carbocation, and then the chlorine anion is going to add to that, and we'll get our product. So that's the mechanism on how these work. Okay, moving along, we're going to look at the addition of hydrogen halides to alkynes. Nothing new here. It's the same as what we did with the alkenes. The only thing you'll have to watch is how many equivalents that you have. Now with the hydrogen halides, this could be any of the halides here. Maybe I should just show this as HX. And so the X can be either fluorine, chlorine, bromine, or iodine. We're not looking at a halogen molecule, it's a hydrogen halide. So the hydrogen halides are a strong acid, and any of them will work here. Let's look at our mechanism and we'll see what our product is going to be. You'll have to pay attention as to how many equivalents of the hydrogen halide that you're using. Mechanism, strong acid, we look for something to protonate. We're going to protonate the triple bond. You'll get electrons come out of the triple bond to grab the acidic hydrogen. There's partial positive charge on it. This will follow Markovnikov's rule, kind of, because he says, you know, when you're adding to an alkene, the hydrogen goes to the carbon with the most hydrogens already on it. Same thing will apply here for the alkynes. As far as which one gets the hydrogen, which one going to get the halide, the hydrogen will go to the one with the most hydrogens already on it, because you're trying to get the most stable alkene. We want the more substituted for the carbocation. You want some stable carbocation. And so we want it on the more substituted carbon. We had kicked off X minus here, so whether it's a fluorine, bromine, or chlorine, whatever we happen to be using, and that adds to the cation. Now, we would stop here if there's one equivalent of HX. If there's two equivalents, we'll go again. If there's two equivalents, we go again. Going to protonate the double bond, still following Markovnikov's rule. Hydrogen go with the carbon with the most hydrogens already on it of the double bond. So we have the carbocation. You're always wanting the more stable carbocation. And then the halogen that we kicked off, that will add to the carbocation. And there's our product with two equivalents. Of HX. So you'll have to pay attention whether you have one equivalent or two equivalents. So again, this did follow Markovnikov's rule. That section also talks about getting anti-Markovnikov, and we're going to talk about that in chapter 10. So we'll hang off on that, just like I did with the alkenes. I said the same thing for the alkenes. I said we would hold off until chapter 10 on those. Now, we also did the halohydrins with alkenes, where we had the halogen and water. You can't do that with alkynes. There's something else that happens with those, and so you can't make halohydrins if you're doing an alkyne. So that one is different. We can't do those with the alkynes, but with an alkyne, we can add hydrogen halides, just like we did with the alkenes. You can do those with an alkyne. Only difference, you have to pay attention whether you have one equivalent or two equivalents. And then we can also do the halogens that I just did in the previous section. Again, you have to pay attention whether you have one equivalent or two equivalents. That's the only difference between the alkynes and the alkenes. They still work exactly the same. Questions on those? Okay, we're going to go back to section 14. And section 14 is looking at carbines. What is a carbine? A carbine is a divalent neutral carbon. Here is an example of a carbine. We'll look at different carbines, but here is one example. That carbon is divalent. You see there's only two bonds, and it is a neutral carbon. If you calculate the formal charge, you'll see that the formal charge is 0 on that carbon. Now, we know carbon wants to be tetravalent. So as you can imagine, this is a very, very unstable species. It's very reactive. Very unstable, very reactive. You are not going to be able to make a carbine and filter it out, weigh it, put it in a bottle, and keep it. It's not going to last. They usually only exist for a few seconds. So we're going to make carbines, but we're going to have to use them very quickly for something. Let's take a look first at how to make a carbine, and then we'll look at a reaction that they will undergo. One way to make a carbine is from diazomethane. This is diazomethane. Diazomethane is a stable molecule because it's got resonance. Let's just draw a resonance structure. You can draw resonance for it. We can move electrons away from the negative charge. So here's a resonance structure you can draw. So it's going back and forth between the two resonance structures. So it's a pretty stable molecule. So you can actually we can order and buy diazomethane. But if you take diazomethane and you heat it up or shine UV light on it, heat or light, it will break apart. You get a nitrogen molecule, and of course a nitrogen molecule, that's just a gas. You get nitrogen gas, and that will bubble out. And the other product that we get is the carbine. Now, like I said, carbines are not very stable, so we need to use it very quickly. So normally what is done is you prepare the carbine in situ. Now, what does in situ mean? In situ means you prepare it in the same flask as what you want it to react with. So we're going to make it in the same flask as I've already got what I want to react it with. So as soon as it's made, it can react. Because we know it's not going to exist for very long. So you got to have what we're going to react it with there in the same flask, because it only exists for a few seconds. Now what we're going to react it with is alkenes. So let's take an alkene. And I'm going to put in the diazomethane. And we'll either put heat or light. Heat or light, of course, breaks the diazomethane apart. That's going to make the carbine. So this is preparing it in situ. We're making it in the same flask as what we're going to react it with. So as soon as the carbine is made, there's our carbine. The carbine reacts with the double bond. And this is the mechanism on how it reacts. You're going to get that pair of electrons that's on the carbon. They're going to go to one of the two carbons of the double bond. It does not matter which one you go to. Then we're going to keep from breaking the octet rule, we take a pair out of the double bond, and those are going to go back to our original, what used to be the carbine. So we're just moving electrons around a little cyclic array. They're just moving around between those three carbons. Our product that we get to follow that is you make a cyclopropane ring. We get a cyclopropane ring out as a product. So there is one carbine that we can do. We react them with an alkene and we always make a cyclopropane ring. Questions on that? Now, in this reaction, with the example that I had, we created, nope, never mind, I misspoke. There is no chiral center on that, so that's the only product. Let's look at one that could potentially have some stereochemistry. There's no chiral center in that one, so there is no, you don't have to worry about it in answer. It's an achiral molecule. Let's do this alkene. And again, we're going to do the diazomethane. And either heat or light. That gives us the carbine. And then the carbine reacts the same as it did before. I'm just going to go ahead and jump to the product. Now, all of this happens at exactly the same time. We're forming a bond here and breaking this one and forming a bond here all at the same time. So our stereochemistry is locked into place. Those methyls started on the opposite side, they will be on the opposite side in the product. If they were on the same side in the starting material, they'll be on the same side in the product. So we keep that same stereochemistry. You can see we had the trans, they were on opposite sides, they will be on opposite sides here. So you can see I got one as a dash, one as a wedge. Now, with this one, we do have the chiral centers. So is that my only product? I told you when you get chiral centers, look to see if you have a plane of symmetry between those chiral centers. Is there a plane of symmetry between the two chiral centers? No. So that means I've got an enantiomer here as well, because I've started with an achiral molecule and I'm making a chiral product. And so we have to worry about an enantiomer then. This will have an enantiomer. Because I brought my carbine in here on the bottom for that one. I brought it in from the bottom and reacted, but the carbine could have come in from the top because that alkene starting material there is flat. It doesn't matter whether the carbine comes in from the bottom or the top, it's the same thing. So that's why we get the enantiomers. You get a pair, you get a racemic mixture, you'll get a 50-50 mixture of the two enantiomers if we have stereochemistry. Previous example, there is no stereochemistry, so that's my only product. We don't have a chiral center. Questions on that? Let's look at another carbine. We're going to look at making carbines by alpha elimination. And with this one we start with trichloromethane. Common name for this is chloroform. You've all heard of chloroform. That's the common name. IUPAC would be trichloromethane. If we take chloroform and react with a strong base, any strong base, I'll use potassium hydroxide, but any strong base will work. Our strong base is going to grab the hydrogen off of the chloroform. That's a reasonably acidic hydrogen because all those chlorines are pulling the electrons away from that hydrogen. You got 3 chlorines that's pulling electrons away from the hydrogen, so that makes that reasonably acidic. And we get this anion. Potassium would balance the charge out. We'd also have water because the OH grabbed the hydrogen, that made a water molecule. We're not concerned with that. Now, this is in equilibrium with a carbene. If one of the chlorines leaves off by itself, then we get a carbene. The chlorine just left off. Potassium is balancing the charge out, so we get potassium chloride, a salt, but we've made a carbene. This is alpha elimination because this is the alpha position right there, and so we just eliminated the chlorine off of the alpha position. That's why they call it alpha elimination. So we've made a dichlorocarbene. Now we can do the same reactions with it as we did with our previous, just like we did with the previous example, the previous carbene. You still do it in situ. So I'll do the same alkene that I had up there a moment ago. So I have my chloroform here. That's in the condensed formula. And we need a strong base. I'll mix it up here. We'll use sodium amide. Any strong base will work. So I'll use a different one here. So we again do this in situ. You prepare the carbene in the presence of the alkene that you want to react it with. So this is going to make the dichlorocarbene. And that reacts with our alkene, and we're going to make a cyclopropane ring. The only difference is it's still got the chlorines on there. Is that my only product? We've got a chiral center right here. This is a chiral molecule. So this one would also have the enantiomer. See, in my other one, I didn't have that one. I had 2 hydrogens out there instead of the chlorines, because then you had symmetry through the molecule. We didn't even have a chiral center. Here we have a chiral center, so you'd also have the enantiomer. Now, we got one more. So the only difference between this one and the previous one is this one's got chlorines, whereas the other one had hydrogens out there. We're next going to look at the Simmons Smith reaction. This is named after the 2 guys that discovered it. As we go throughout the summer, we will see some reactions that has somebody's name associated with it. Especially in organic 2, we see a lot of named reactions. Those are normally your most important reactions. So make certain that you know a named reaction. Those are extremely important. Many times they're important enough that the guys or woman won a Nobel Prize for the work. So it's some of our most important reactions will have somebody's name associated with it. So make certain you know named reactions. That will be useful for that ACS exam that you take at the end of Organic 2. Any of the named reactions, I can just about guarantee you they'll have one of those on there, of each that we cover. Those are things that you'll likely see on DAT and MCATs and things like that. Those named reactions are our most important. Now let's see what they did that was so important. They took diiodomethane and a zinc copper alloy and found that this made the zinc winds up inserting in between one of the carbon iodine bonds. And you get this species. This is called a carbinoid. It's also referred to as the Simmons Smith reagent. I left an S off up here. It's Simmons, not Simmons. Simmons. This is the Simmons Smith reagent. It's called a carbinoid. A carbinoid is something that reacts like a carbene, but it's not a carbene. This is much more stable than a carbene. You can actually make this carbinoid and put it in a bottle and keep it for a while. It will last for a little while. It's not as unstable as the carbenes, but it will react just like a carbene. it will react just like the original carbine that we did with 2 hydrogens on there. It's going to react just like that carbine. It's going to do the exact same thing as what we did with that carbine. So let's look at an example. It's still, most people will go ahead and prepare it in situ, but you don't have to because it's a lot more stable. So here I have diethylmethane, I have zinc metal, we have a copper chloride. The zinc and the copper will form a zinc-copper alloy, and that's what goes ahead and makes the carbenoid. So again, this is going to react just like that carbene, and so we make a cyclopropane ring where the double bond was. There is our product. Now, is that our only product? Do we have any enantiomer? No. That's got a plane of symmetry through it. So there is no enantiomer. I do have chiral centers, but it's an achiral molecule. You have a plane of symmetry through there. So that's our only product. There is no enantiomer. So we would have gotten the exact same product if I had done the diazomethane. If you use the diazomethane, you get the exact same product. It's going to go through that carbene and we're going to get the exact same product. Now if we'd done the other one with the chloroform, put that one down here. If you use the chloroform, it's the same thing except there's 2 chlorines on there. So you have to pay attention. That one won't have 2 chlorines on there because it makes a dichlorocarbene. So that's the only difference. These 2 work exactly the same. They give the same product. Questions on the carbenes? So your carbenes always make a cyclopropane ring where the double bond was.
Is the alpha elimination only with chlorine?
Yes. We only do the chloroform. Bromoform is not acidic enough to get that hydrogen off to get it to work because it's not as electronegative as the chlorine. So we only do the chloroform. We're only going to do it to make the dichlorocarbene.